Soil temperature is important to a wide range of chemical, physical, and biological functions in soils. The growth of biological systems is very closely controlled by soil temperature, and soil temperature also affects the growth of plants. It affects seed germination rates and root growth, but soil temperature also indirectly affects plant growth as it influences the microbial populations of the soil. It influences organic matter decomposition and mineralization, that is, the freeing up of soil nutrients, as well as the organic matter accumulation. It also affects biodegradation rates of things like herbicides, pesticides, and other compounds. And we can measure the impact of all this on soil biological activity in terms of soil respiration, which is the production of CO2 and consumption of O2 in soils, which tends to peak around 40 degrees Celsius. But soil temperature also indirectly affects plant and microbial activities in soils by affecting the soil hydrology. Remember that viscosity, water density, and soil water tension are all dependent on soil temperature, and temperature will affect how water flows in soils. And lastly, over long periods, temperature has a critical influence on chemical weathering or mineral weathering and soil formation. Remember that for every 10 degrees temperature increase, weathering rates about double. Soil temperature is quite variable, but it does vary in a characteristic manner on a daily and seasonal basis that is, of course, coupled to air temperature. But to explore this coupling a little more, let's look at some data. Here we have soil temperature data for Norman, Oklahoma, measured in March of 2020. We have a brown line which is showing soil temperature measured under bare soil surface. We have a dark green line for soil temperature measured under vegetated surface. And then we have a couple other lines, including the black one here at the bottom, which is soil temperature measured at greater depth here under the vegetated soil in 60 centimeters depth. So we can draw three lessons from the data that we see here. The first one is that vegetated or soil cover in general tends to reduce soil temperature fluctuations compared to the bare soil. We also see that the temperature fluctuations decrease with depth. So if you just look at the green lines of under the vegetated surface as we go from 5 centimeter depth to 10 centimeter depth, 25 and 60 centimeters depth, the temperature peaks get flattened out. We have less fluctuations in temperature. And the other thing we see in here, but you have to look a little more closely, is that if you compare to where in time the peaks happen, you'll see that as we go to greater depth, the peaks happen later in time. So there's a lag in that temperature change that is observable with the depth. So solar radiation received at the Earth's surface may be either absorbed or reflected. And the radiation that is absorbed is converted to a thermal energy, which then causes or may cause a rise in temperature. Reflected radiation, though, is sort of a loss of heat if you want to think about it this way. Thus, the warming effect of solar radiation depends very much on the absorptive or reflective properties of the surface receiving it. So solar radiation tends to warm dark-colored soils more readily than it warms soils that are lighter in color. That is because lighter colored soils have a higher reflectivity. The energy that is absorbed at the soil surface results in soil warming if the absorbed energy exceeds the amount being lost. It can be lost due to evapotranspiration, that is the loss in latent heat, or the loss in sensible heat. Well, and we have a positive energy balance at the surface normally during daylight hours when we have a high level of radiant energy that is being received from the sun. The net result then is a rise in temperature at the soil surface above the temperature in the subsoil, which causes then a downward flow of heat, and that heat is being accumulated in the profile. At night, though, this whole thing reverses, and we have more energy being lost than is received at the soil surface. So as a consequence, the surface of the soil cools during the night, and the temperature drops below that of the subsoil. And heat which was previously accumulated in the profile during the day flows back towards the surface to be lost mainly again as infrared radiation. The net heat transfer between the surface and subsoil during any 24-hour period is in part a function of the amount of solar energy received during the daytime and in part dependent on the ability of the soil to transmit the heat downward during the day and upward during the night. This heat transport can be by mechanisms of radiation, which is really insignificant in soils, by convection, which can be important if you have water movement or significant air movements in soil, but mostly it is going to be due to conduction. And the conduction of heat results from the exchange of thermal energy, which, if you remember back to your physics classes, really is the motion of molecules and the kinetic energy of those molecules. So the conductive heat flux is expressed mathematically quite similar to the one that we've already learned about for water flow in soils. We have a flux density, so a heat energy throughput through a cross-section area per unit time in response to a temperature gradient, meaning a temperature difference over two locations with some separation L, and it's all moderated by a thermal conductivity lambda. Now, the thermal conductivity in soils tends to be highest for the soil particles, closely followed by water. The difference about a tenfold difference between the two, quarts higher than water. And the other constituent in soil, air, has a really, really low thermal conductivity, which is why we use air as insulators. Now, if we have not soil, but just a chunk of quartz, and we impose a temperature gradient over this quartz, we get a relatively high flux of heat through that quartz as a solid medium. However, soil, as we know, is a porous medium, and here, because we're talking about the mechanism of conduction for that heat transport, the transport is really only occurring where we have contacts between the solid particles. Meaning that in soils, it is very much the number of contact points that limit conduction of heat. Now, the number of contact points is going to depend on particle size, particle shape, arrangement, and density of that particular soil. Now, if we go further and we introduce water into our soil, we see that our thermal conductivity, our overall thermal conductivity, tends to increase as we increase water content. And that is because, well, now rather than be limited by small contact points between particles, we've increased that area. We now have flow going through the solid and the water phase. So we have more contact points and we have a larger volume through which this conduction of heat energy can occur. Okay. So to summarize this, we can put this in a plot and say, how does the soil thermal conductivity change as we change the water content? So if we look at a sandy soil, we see that, surprise, surprise, the thermal conductivity increases as we increase the water content, but that the effect of that increase is highest in the beginning when we start to introduce water into the soil. But later, as we go closer towards saturation, the added benefit of having more water in the soil is diminished. If we compare that sandy soil to a similar sandy soil, but one that has been compacted, we see that the compacted soil has a higher thermal conductivity. And that is because as we compact the soil, we create more contact points, thereby increase the thermal conductivity. Now, a finer textured soil will tend to have an overall lower thermal conductivity, but it will be less dependent on water content than maybe a coarser textured soil. So now let's compare a dry soil and a wet soil that are exposed to the same radiative forcing. We know the dry soil has a lower thermal conductivity than the wet soil, and we also learned that water influences the reflectivity of soil, where if we have more water in the soil, more of that radiative energy is being absorbed versus a dry soil which will reflect more of this energy. So in the dry soil, we would expect that flux, that heat flux, to be reflective of more energy being reflected, so less energy available to heat the soil, plus we have a lower conductivity, which means that heat transport is going to be slower. If we look at temperature profiles as a function of time, and this will be for relatively close to the surface, we would see that for the dry soil we have large temperature swings between day and night, versus for the wet soil that response is very much muted, where we have a more dampened response. Now why is that? And it's not really consistent with what we've learned so far. And the reason for that is that we're actually missing a piece of the puzzle, and that is the volumetric heat capacity. So in addition to the conductivity, soil also has a heat capacity, which is a storage mechanism, or one way to look at this is the amount of heat needed to change the temperature of a substance by 1 degree. So it's not just about how fast we can move heat energy in the soil, but also in order to actually see a temperature response, how much of this heat input is going to be stored before we see a change in temperature. Now, of the constituents in soil, air has a relatively low heat capacity, just as was the case for thermal conductivity, but water is the constituent that has the highest heat capacity. And we've previously looked at properties of water and anomalies of water, and this is one of the things that we've looked at, that water has a really high volumetric heat capacity, which is also one of the reasons why it takes so much energy to heat up a pot of water on the stove. So if we add the heat capacity to our comparison of dry and wet soils, the dry soil, low heat capacity because there's not much water there. Wet soil, high heat capacity. Now it's this high heat capacity which is responsible for that wet soil being very slow to heat up, because the radiative energy goes towards the heat capacity and not towards an increase in temperature. So in comparison, we would, for a wet soil, see lower temperature fluctuations at the surface, and at the same time a higher heat propagation into the subsurface, which means that subsurface layers are faster to heat up in the wet soil than they are in the dry soil. Now add to this one more piece which isn't depicted here, and that is evaporative cooling. So the wet soil would also lose more of this energy because of evaporative cooling. That's all dependent on the atmospheric conditions, so that'd be another complication. So to take all this together, it's not just the conductivity, but also the capacity that informs the actual temperature response that we see in soils. And we can put this in a graph that takes the ratio of conductivity to capacity and looks at how that changes with water content. And you will get this kind of characteristic shape. So if we go from a dry soil towards the peak of this curve, we would see that if we increase water content, we would increase the conductivity and we would have less of an impact of the capacity slowing down net transport of heat. Versus if we're to the right of this, now the heat capacity term grows faster than the conductivity term, and we would have a decline in this response. Essentially, this is all being taken together to look at heat transport in a diffusion type of equation, in which then the ratio of the conductivity to the capacity, in addition to the density of water, is termed the thermal diffusivity. But if you're interested in this, take a soil physics class.